Hey everybody, my name is Josh Adkins, this is Kyson Montag and John Schaefer, and today we're going to be telling you about our fully integrated smart home project. First we're going to discuss a brief overview of the project, and then move on to the engineering requirements, and then take a look at the block diagrams of the system architecture, and then take a quick look at the project timeline through May of 2013.
The objective of this project is to provide a complete affordable home automation solution by transforming the house into a smart home. Although the idea of a smart home is not a new one, with products such as Inseon and Control4 already available, installing a complete home automation system today can cost hundreds, if not thousands of dollars. Our goal is to provide consumers an affordable way to control and monitor many aspects of their home from a universal, accessible interface that incorporates an intuitive user interface available on any internet-connected device.
Our system will provide users with a low-cost home automation system that is easy to install, configure, and control. The system will allow users to manage the devices, outlets, and power consumption throughout the home from a user-friendly interface. The system will offer users a way to monitor the current and power dissipated by each appliance connected through a system node. By allowing users to track their power usage, configure energy settings, and remotely control their home environment, we hope that our system will help consumers save energy and encourage greener lifestyles.
The world we live in is becoming more connected every day. With the affordability of powerful mobile computing devices, consumers can remain constantly connected to the world around them. People can effortlessly interact with their environment on the go. However, we feel that a major environment has been overlooked. Our challenge is to provide a simple, cost-effective solution for monitoring and managing the home from any internet-connected device.
Let's begin by going over the engineering requirements that will dictate the overall design and desired feature set of the system. We want to make sure that the system is fast enough to comply with user needs in every mode of operation. When syncing client nodes with the server, we will require that properly functioning nodes register within 30 seconds. For transmission of user commands, we will require that the system response time, defined as the time delay from when a control command reaches the front of the event queue to when the desired event occurs, under normal operating conditions, will be no more than 500 milliseconds. Additionally, when devices are configured to utilize the sleep timer functionality, the desired operation occurs within 5 seconds of the user time specified.
Because we have chosen a model that incorporates low-cost microcontrollers, which typically have smaller amounts of available flash memory, we will require that the memory footprint of all the controller code at each node remains under 16 kilobytes. Additionally, the code that drives the RF transceivers is less than 8.
We have chosen to implement at least 2 separate user interfaces, such as the administrator or normal users, with differing options and features, and individually configurable settings.
To maximize the usefulness of data reported by sensor nodes, we will require that temperature sensors are accurate within plus or minus 5 degrees in the range of 20 to 110 degrees Fahrenheit. Also, the power consumption measurements have to be within 20% of the nominal value.
To ensure system reliability, we will require that 90% of all valid requests to the internet-facing server are handled without exception. We also require that 90% of commands issued to a node are handled without any errors.
Because we want our system to integrate easily into the homes of users, the client nodes will have the ability to be powered by a standard 120 volt AC 60 Hz outlet. In order to meet our goal of developing a system that is both powerful and affordable, we have designed so that the cost of each client node will be less than $20 in large quantities. To ensure system safety, system nodes will open the power path and alert user if current draws over 10 amps. Along with this, if temperature exceeds 75 degrees C, power path will also be opened.
To ensure system usability, we will hold usability testing. During the usability testing, we will require that 5 test subjects are able to perform the following tasks. A new user to the system will be able to sync a new node to an existing system, toggle the state of a specified device in a usable system,
Now that we've finished addressing the engineering requirements, let's take a closer look at the system architecture. The diagram shown depicts a black box representation of how the system interfaces with its environment. Users can provide input in one of two ways. Through the user in path, they can issue a command that results in the action associated with that command being output through the action out path. In the other option, users can query the status of a device. Environmental information can be read through env in, and then the user receives data back through info out.
Taking a closer look at the system, we can see that the system itself is comprised of a main control unit and several wireless nodes. Feeding into the system, we have user input, client requests, and data out. User input comes from the top level block diagram as you've seen before, and this is any request that the user might be interested in making. This is to either control some element of the home or perhaps request for some information regarding temperature or power consumption in the home. Client request is any request that comes from a client activated device. This is anything such as a iPod, iPhone, anything of that nature. Data out is any data that is to be relayed to the user from the system itself.
The node level block diagram shows a lower level representation of how the nodes interface with the system and can be viewed in three primary stages. The transformer and rectifier stage receives input from the power outlet and is responsible for converting the AC signal to a DC signal and stepping down the voltage to a level that is usable by the microcontroller and transceiver. Because the transceiver and microcontroller require different voltage supplies, two different regulators were used to produce the desired input voltage for each. The transceiver is responsible for sending and receiving messages from the main control unit, and the microcontroller is responsible for interpreting these messages as commands and executing the behavior associated with each node.
The last piece of the node is comprised of the components used to control and monitor the AC power path. The first component is a relay that is controlled by the microcontroller and is used to turn devices in the home on or off. The second component uses a current sensor, which uses a Hall effect to measure the amount of current flowing through the device being controlled. This information is then relayed back to the main system control unit and is used to calculate the amount of power being consumed by the device. Aggregating this information from all nodes in the system will produce a real-time power consumption profile for a home or specific device. We hope that this feature will encourage users to turn off devices when they are not in use, ultimately contributing to a greener, more eco-friendly planet.
We have developed a project timeline with important milestones to track our progress throughout the duration of the design process. Let's take a quick look at our projected schedule through the end of the academic year.
The timeline begins on November 12th with the release of this presentation. On November 19th, protoboard and circuits will be completed. These will be used to test the base of our idea. At the end of the term, December 3rd, a transceiver prototype will be completed, along with the final design assignment finished. The final design assignment will include schematics, PCB layouts, and pseudocode. On January 21st, server-client interaction will be established. Following, on February 18th, node behavioral code will be completed. On March 18th, server and client code will also be completed. April 8th, we will start the stage of testing for this project. This will start with performance and reliability testing. On April 15th, usability testing will begin. Our project will finish on April 22nd, followed by being placed at the Cornell Expo on May 3rd.
To conclude this presentation, I would like to summarize some of the main topics that have been discussed over the last several minutes. In today's world, people are becoming more connected to their devices and their environments than ever before. The unfortunate truth of the matter, however, is that the home has been sorely overlooked. There are several home automation solutions already on the market today, however none of these solutions cater to the needs of the average consumer, which wants a simple, easy-to-use solution that is reliable and affordable. As such, our goal is to create a system that meets all of these consumer needs. We briefly discussed the engineering requirements that we believe are necessary to successfully complete this project. We then gave a brief system overview that uses blocks diagrams showing how the system interfaces with itself, the environment, and the user. We then presented a proposed timeline that gives a general project roadmap through the early lifespan of the project. I hope this project presentation helped you more fully understand what our goals are and how we intend to achieve them. Thank you very much for watching.